Hello and welcome to this short video demonstration on how to maximize the frequency of a body in white using PBARL's, Topometry and the new MDISPR function in Genesis 19. So just to review this model first of all, on screen you can see some PBARLs. I'll just put the whole model on screen. So we've got an example for torus, and for this example we've used the Lattice mesh generation tool to create orthogonal lattices. We have just one property, so I can actually just show only these on screen now. And if I view these in 1D style, you'll see if I zoom in, they are tubes. And there's the cross section that we have in place. And I can take a look at those inside the group properties menu, PBARL. So here we're using the Genesis CS Library 1 approach, which is the tube that is controlled in its dimensions by an inner diameter D1 and then a wall thickness D2. Taking this approach makes the design data a little cleaner because if you do use the Library 2, which is perhaps more typical, then when we do get to the tube option, if I can show that for a moment, then we have D1 and D2, which is actually useful for some other factors, but for designing it's more complex because you have to link these design variables together. Otherwise they can create infeasible dimensions. So go back to CSLib1 and a tube, and in fact I'll just cancel that so that's finished. Okay, so they're the lattices. They can be created in any tool you like, really. If you've got them from another source, then that's absolutely fine to use those. One note, if you're going to perform optimization in Genesis for what we often describe as bars or beams, they must be bar elements, so that's the PBAR and PBARL formats in place of the PBeam and CBeam. And that's because the design data is only associated to the PBAR format inside Genesis. Okay. So some other things just to note is the loading we've got in this model. And we're going to optimize for the torsional excitation. So we've got forces in positive, and this one, whilst it's viewed as positive, is actually out of phase by 180 degrees. So it's creating a torsion loading. And what we want to do is we want to use frequency response to identify the first torsion mode. If I just take a look at the results in the model, you can see here are the modes. I know this, having looked through already, is the first mode. I should just add this is with the lattices not in place, like so. This is the mode that we want to identify, but it could easily be confused with the second mode or third, and so you start to see some unclear natures. So we're going to optimize for this first mode, but we're going to use the frequency response approach for that. So just to view what we're going to try and do is we'll create a plot, and here we can just add our solution. So torsion is our load case, 4 is bending, but we're not considering that in this option. I'm just going to look at the motion of this first grid and translation in 3, and you can see here this is what we're going to optimize for. And what we're going to use is the MDISPR response, which rather than looking at the amplitude in the frequency response graph, we're looking at the x-axis and the frequency at which the highest point in this graph is achieved. And you can see here, so for this one it would report out 25 Hertz very clearly. And then we can use that response either as an objective to maximize or minimize, or we could additionally set that as a constraint, so we could put a lower boundary constraint, for example, of 30 Hertz, and then minimize mass on the solution. But in this example, we're going to maximize the frequency for a given mass, just to demonstrate the process. Some other tips for this approach are when we want to make sure we pick the first peak as the highest peak. Sometimes secondary modes can have a higher amplitude depending on the behavior of the system. So a small trick that can be helpful is to change the damping that's applied to the model. So in this example here, what I've done is change the damping from a constant 3% of critical to a damping ratio that starts at 3% of critical at 0 Hz, and as we increase to 100 Hz, that's increasing to 12%. And so tuning that on the baseline model is useful to make sure that we always achieve the first peak as being the highest peak, which is what the response will monitor. Okay, so let's take a look at the design data now. So if I put everything back on screen, we want to optimize the diameter and thickness of each of these beams. We want to do so independently, so each beam is considered on its own. So we can do that using topometry optimization inside Genesis. So to set it up, first of all, we just need to create our design variables. So I'll create one for diameter. And here we're going to start with an initial diameter of 50, a minimum of 0.1, and a maximum of 100. And then the next we will do is the thickness. And this will be an initial thickness of 0.5, a lower boundary of 0.1, and a maximum of 8. But you can choose what you like for these. Next we assign those two design variables to our PBAR. So here we choose the type. You can actually, if you wish to, change the section type in the design data compared to the actual analysis model, but here we'll just keep it as common, so tube, and the D1 diameter is selected, and then the D2 thickness is selected. So that's now applied the design variable to each of these to this property. Next we want to activate topometry that internally is going to divide the model into one property per element, making the design freedom much greater, so we can see where it needs to change the design. So the way the topometry interface in Design Studio works is that once you enter it, any property that has already been defined with sizing will be available here to add the option of topometry. So you can see this is our PBAR, so I'm going to add that. And next, based upon the global coordinate system, I'm going to add mirror symmetry, like so. And note actually, the way this mirror symmetry works is to look for elements on the left and right hand side of the plane within a tolerance to make sure that they are paired, and then they will be maintained as the same patch. Now, when I built this example, I did it very badly, and unfortunately the elements are not exactly symmetric. So we can try to improve that by just changing to be centers only, and put a tolerance maybe of something like 2 millimeters, so it's a bit more approximate in our checking of mirror symmetry. That's a useful tip. Okay, so that's now defined, and that is all the design variable data created. I'll take a look at what's created in the input file when we're all finished. Next, I'm going to define my objective, which is for this study going to be using the MDISPR response. And here, so we'll go to more responses. And before I do, I must make sure I change the objective to maximize, so it's going in the right direction. And on the next page here, we want to look for dynamic displacement as an option. And here, if we scroll down, we'll see this resonance from modal MDISPR response. Okay. And then we choose our component here. And I've already renumbered the node in question to be number 1 because it's attached to an RB3 inside here, and I wanted to just avoid having to hide away the elements. And typically you'll tend to know the node you want, so you can type it in and add it here quite happily. But of course you can pick it off screen. So we've got the Z displacement of node 1, and we'll do that for the torsion mode. So that is now set to maximize. And the constraints for this, because we've got a maximizing option for the objective of a performance. We'll put a fixed mass, and I'm just going to put a 5 kilogram mass here, so we're in tons. Oops. For the PBARL group, and that's done. So that is the optimization set up to maximize the frequency for 5 kilograms of beam elements. Some useful tips I'll do just to show you are in the output requests to make sure we've got the right outputs set. So a useful thing is analysis output. If we set it to either first and last, which reduces the data a lot, or every 5th cycle is quite a useful option. So you can see how the optimization is progressing as it's running without using too much disk space. And then file control, what we also want to do is request this updated input file, and we'll do that at first and last. And this is a bulk data file that shows the properties in their current iterative state. So cycle 0 will show you the model, but it'll also show you it divided into multiple properties. And then last will show you the beam properties as they've been updated through the optimization. I think lastly, we'll just give ourselves a few more iterations than the default of 10 for sizing and topometry. We'll set that to 20. And then lastly, what I want to do is just choose to manage my data that I'm exporting. I'm going to go to Preferences, and on the Export tab I'm going to change Design Data here as an output option as a separate include. So if I've got the model already built as an analysis model, I don't need to manage it all as one. I can just export that. So I'm going to export here into my demonstration folder for you. So this will be Lattice Topom opt1.dat. Okay. Okay, so that's exported. I'm just going to go to Notepad and show what we've got. So in the folder where we've just exported, we have the main file that we've exported. So this one here, the opt1.dat. And you'll notice at the top of the bulk data we have an include statement automatically added for the design.bulk. And when we look at that, this is the input data to do the topometry of the beams. So you can see here we have the 2 design variables, a dvprop3 that connects those directly to the PBARL property, and the dsplit command that is going to divide to create one PBARL CBAR combination for each element or pair with the symmetry that's defined. Then we've got the objective to maximize our MDISPR response. So this is the Z displacement of node 1, and then our constraint on mass of 5 kilograms. Just the last thing to add, if you're doing any of this manually inside the deck, then the output options that would sit in the case control. So we have A print is 5. I've done to have the analysis output every 5 cycles. U print is my update file, which I'll show you in a moment. And then sizing equals post to make sure that we do get the contour plots of diameter and thickness for our outputs. So having created the data, I've now run this optimization remotely on a cluster. Of course, if you're running locally, you can just submit it here from Genesis Optimize. To post-process the results, what I'd like to do is not only view by color the diameter and thickness of these beams, I'd also like to view how they look on screen in terms of the visual diameters. So I'm just going to utilize the update file for this. So we can have multiple models imported inside Design Studio. So I'm going to go to my previously run results, which is this Lattice Opt2 that I've run, and actually import the update.dat file. So update 10 means it finished at cycle 10, and this is the updated file. So I'm importing this as a new model, like so, and you'll see now as we zoom in on this model, that the beams are all in different property groups, and that's what the topometry has done for us. So what I can do next is I can import the results. So I'm going to import the Opt2, Lattice Opt2 post 10 results. And lastly, just so I can look at the results a little better, I'm going to import my Lattice Opt2 analysis results. Just need to find them. There we are, Lattice Opt2, cycle 10. And because I'm in a new model session here, and I'd like to create a plot that combines to my baseline results, I'm also going to import my baselines into this particular session. So I'm going to go up to my baseline folder, and I'm going to read this one here. Okay, so let's just take a look at what we've got. So if I want to view these beams on their own, a useful way to do that is, rather than using show hide groups, it's to use manage groups. And here I can just choose my filter to only list PBARLs. In fact, I need to go to the top and down to the bottom. And here I can now right click and choose show only the selected groups. I'll deselect them. And on the display, I'm going to view them as solid representations, and you can really see here how the beams have gone to their different diameters in the solution. Okay, and then a lot of beams are right down at their minimum properties. So next, whilst viewing in this 3D mode, I can overlay the results in terms of the diameter or the color. So you can see here I've got my PBARL cycle 10 D1 dimension. So you can see these match very visually with the diameters that you're seeing on screen. The thickness is more tricky because of the small section size compared to what we have. But if we want to do a color, we can start to see the diameters, and most of the diameters have gone down to the minimum. Not in all cases, some have gone up to 0.5 or even in some cases nearly 1. But interestingly, they're very much not going to the maximum allowable of 8 millimeters. And here, if we want to hide any results, so any diameters under a certain amount, we can just simply choose a value to slide them by. We can key that in if we want to. But anything less than maybe 20 millimeters is off screen. So we can look at those, and then we can overlay those with our overall model by putting everything back on screen, like so. Hide those RV3s. So you can really start to see where the improvements are being made. Now you'll note that the symmetry isn't happening in this model. That was something, when I prepared this demonstration model, I did a very approximate job, and my mesh was very asymmetric in the last generation, and so that's why it hasn't found the pairs as it should do. Okay, so that's the process of visualizing it. I want to just leave that now. My next step is just to check the responses, so I'll create a frequency response plot, a new one here, where we can choose our component. First of all, I'm going to add the baseline actually, which is this one here. Grid 1Z, and then I'm going to next add the optimized result. And there you go, and you can see quite clearly how the frequency has increased from 25 Hz to around about 34.5 if you look at the actual point that we're outputting the values there. Okay, so that is how to optimize beam lattices using Genesis's topometry functionality. Thank you very much.